All right, so one of the most basic types of hypothesis tests is a one-sample z-test. It essentially tests whether or not a given sample came from a specific population. So the conditions under which we would use a z-test are when we know the following things. We need to know the population mean. We need to know the population standard deviation. We need to know the sample mean and the sample size. If we know those things and there's only one sample, we know that we're looking for a one-sample z-test. Now, whenever you conduct a hypothesis test, there are really four things that you should do. You should state your hypotheses, specifically your statistical hypotheses. You should set your rejection criteria for the null hypothesis. You should calculate your test statistic, and then you need to end up interpreting your results. So let's work through sort of a sample problem. Okay, and in this sample problem, what we're going to have is this hypothetical scenario where, let's say that we are trying to figure out if a new way to teach reading skills to third graders is an improvement. So we have the standardized test scores from the prior year, okay? And that standardized test scores will give us a mean and standard deviation. And we're going to implement this new reading program to a group of 100 third graders. And then we'll get a sample mean for their standardized test scores. And we'll compare the two. So we essentially have everything that we need. So those standardized test scores have a mean of 75, a standard deviation of 5. And when we give that reading program to this group of 100 third graders, we end up with a sample mean of 77. So really what we're going to ask is this group of third graders that we gave this new reading program to coming from the general population, or are they somehow different? If they are somehow different, it's consistent with the idea that this reading program caused an effect, though we're not experimental design, but we'll talk about that later. So we have the essentially the scene set to use our one sample z-test. So first thing that we need to do this is state our hypotheses. And specifically our statistical hypotheses. The first of which is our null hypothesis, which essentially is going to read, hey, everything that you're seeing here is random chance. And if everything's random chance, we are pulling this sample of 100 third graders from the general population, which has a mean of 75. So stating the null hypothesis in statistical terms, in terms of population parameters, the sample that we're seeing comes from a population with a mean of 75. Our mutually exclusive and exhaustive alternative is that it is not coming from a population with the mean of 75. Now recognize this means it could be greater than 75 or less than 75. So we're in a two-tailed situation. So the next thing that we need to do is set our rejection criteria. Now, the way the z-test will work is essentially we'll use the distribution of sample means to get a z-score for our sample mean, and then use that z-score to get the probability that we would obtain a mean of 77 just by random chance. So when you're doing a problem like this, it often helps to sketch it out. So here would be our distribution of sample means, and let's say it's z-score transformed, so we know we have 0 here, and then we'd have everything greater over here and everything lower over here. So we specifically want to determine if getting this is too unlikely for the null hypothesis to be true. To do that, the first thing that we need to do is decide upon an alpha level. We're going to go ahead and go with an alpha level of 0.05, and specifically we're going to have this alpha be two-tailed, meaning that that 5%, or that probability of 0.05, is divided between these two tails. So we would need, in our critical region over here, a proportion of 0.025 and a proportion of 0.025 in this critical region over here. So we have our two critical regions, just to give a little bit more labeling. Critical regions, which are bound by, if I draw this line a little bit more intentionally to the lines, are critical values. And it's these critical values that we now need to go ahead and find. Now, any statistical textbook in sort of the behavioral sciences has a table of z-scores in the back, the unit normal table. You can also look up z-scores in Excel or in R. You could probably just Google it and find it as well. What you'll find is with a two-tailed alpha of 0.05 that essentially this critical value over here is 1.96. And as it's symmetrical, we're talking negative 1.96. So our z-crit, as it were, or more specifically, the absolute value of our z-crit is 1.96. And if we formally set up our rejection criteria in words, if the absolute value of our critical value is, oh, I'm doing this backwards. Let's try that again. If the absolute value of the z-score we observe for our z-test is greater than the absolute value of our critical value, then we reject the null hypothesis and accept the alternative. So we've stated our hypothesis, we've set our rejection criteria. Now it's time to actually calculate our test statistic. Now, when we go about doing this, first thing to do is go ahead and write out the formula for a z-test. It will help you get through it and take it one step at a time. So in this case, our z observed is going to be equal to our sample mean minus our population mean divided by our standard error. Now we have our sample mean already. We have our population mean already. What we don't have is our standard error, but we do have the two things we need to calculate it, our standard deviation of the population and the size of our sample. Specifically, standard error is our standard deviation divided by the square root of our sample size. So 5 divided by the square root of 100 gets us 5 divided by 10 for 0.5. Now we can go back in and substitute in all the values we need here. So sample mean is 77 minus our population mean of 75 divided by our standard error of 0.5. So when we look at this, 77 minus 75 is 2 divided by 0.5. 0.5 goes into 2. 4 times. So now it's time, now that we've calculated our test statistic, to look back at our rejection criteria and interpret our statistic. So if we sort of lay out all this, and look to interpret, essentially what we find is that our z observed, if we think about our first premise here, is 4, and specifically the absolute value of it is 4. We already set this criteria up early. If z observed is greater than z crit, then we reject the null hypothesis and accept the alternative. When we think about this, z observed equals 4, which is in fact greater than the absolute value of our test statistic, or of our critical value, which is 1.96. Therefore, we reject our null hypothesis, and as our null hypothesis has a mutually exclusive and exhaustive alternative hypothesis, we then have to accept the alternative hypothesis. Now, what does this mean for reading in 3rd graders? Now, what the statistical test tells you is that this sample we're looking at did not come from a population with a mean of 75. Now, one reason that could be is because the new reading program had an effect and improved the reading scores of the individuals in our sample. Now, one thing to note is whenever you look at a statistical test, you have to look in the context of the research design. We essentially have a non-experimental or quasi-experimental design with one group and only a post-test. As a result, we can't lock down say that it caused, the new reading program caused this difference. It's possible, but we cannot say because we do not have all the full control and rigor of an experimental design.